Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. And today I've brought a very interesting problem from David Moran's collection, that is Harvard Problem of the Week 81. Once again, it's a problem based on rainbows. I had discussed primary rainbows in two videos earlier, and today I'm going to also discuss tertiary and secondary rainbows in this. So without much ado, let me straight away get into the problem. So let's see the problem. Okay, so okay. So what's the problem? Let me just read out the problem. So assuming that index of refraction of water is 4 by 3 and that raindrops are spherical, uh, show that the location of rainbow is approximately 42° above the line from sun to you. This is the first part of the problem. Okay. And then if you see a double rainbow, what is the angle of the second one? Sometimes we see two rainbows, so secondary rainbow, we have to find the angle of the secondary rainbow. And what next? Even triple rainbows are possible, although they are difficult to see. Where is the third one? So we have to locate the positions of the primary rainbow, which is formed by single internal reflection, then secondary rainbow, which is formed by two internal reflections, and we also have to locate the position of a tertiary rainbow, which is formed after three internal reflections. And of course we can also talk about nth order rainbows, which are formed after n internal reflections. So we'll see them one by one. If you want, you can give it a try. I'll get into the problem discussion, and I'll also be showing you the demonstration once again, same demonstration, just for clarity of things, how I'm going to draw the diagrams. I'll show you some demonstration. Okay, so let me get into the now demonstration. Okay, so okay, so here is this Wolfram demonstration project. Once again, the same figure you might be familiar with, that I had done when I showed you the primary rainbow discussion. So now what is happening here? So this once again, the sphere is this is the figure for primary rainbow only, but the same thing I will be extending for secondary and tertiary rainbow. So what's happening? See, the so many rays are falling. So these red rays are the rays which are coming from sun, and I've shown as if sun is at the horizon level. So these rays are all coming horizontally and they're falling on a water drop, right? And then they are getting internally reflected. And why is the rainbow being formed at a certain particular angle? You see, as I told you earlier, these rays are divergent here. You see, the first ray and second ray are divergent, like these two are divergent, but somewhere down the line these rays have become convergent. And that means what? Somewhere the rays will also become parallel, and when the rays become parallel to each other, then their intensity does not decline even when the rays go far away from the drop. And that's why we are able to see, let's say these are red color rays, so then we'll be able to see red light even far away from the drop. So that's what causes the rainbow. Now I'll just reduce the by the way, what's happening as these different rays are falling, you can see, I'll just show you the normals. You see, here I've drawn all the normals. You see, the angle of incidence is increasing as the rays are going up and up. The angle of incidence, see here, this is the angle of incidence, so pretty large, and as the ray comes down, the angle of incidence is becoming smaller and smaller. So this is the angle of incidence as these rays are going up. Okay, and one more thing I want to show you. I want to show you that this ray diagram is symmetric about one angle bisector. I'll show you which angle bisector is that. So what I'll do, I'll reduce the number of rays. Let me reduce the number of rays to 1. So just consider a single ray, okay, and let me okay, let normals be there. So so if you just consider the bisector of this this green line and this blue line, you can see that this whole diagram is symmetric about this normal, the normal of this angle, right? So let me turn this ray diagram also to show what I mean, the symmetry. So let me just change the incidence angle, just a sec. So yeah, see, somewhere I want to stop in this configuration. Yeah, now you can see this is symmetric about the horizontal line. So I'll be, for sake of easy understanding, I'll be drawing the drop diagrams in this configuration where the incident ray and the exiting ray are symmetric. Another thing you can see is, if this angle is beta with the normal, then this angle is also beta with the normal. And again, all the radii are perpendicular to the sphere. So this angle is also going to be beta, this angle is also going to be beta. So I am going to use the fact that every incidence angle inside the sphere is going to be beta. So I hope this diagram is pretty clear. Okay, and I am going to make all the diagrams in this symmetric kind of configuration where there is only about the horizontal there is symmetry between the incoming ray and the outgoing ray. I am going to draw that kind of diagram. Okay, so now let me go back to my explanation. Okay, so let's see. Okay, so let me just scroll. By the way, this is the handout from Harvard Problem of the Week 81 solution. So I'm using it directly from there. Okay, so here you see this is the incoming light from here, and then it's getting refracted, and then it's getting reflected from here, and then again it's getting refracted. As for the case of primary rainbow, only one reflection. So why I'm doing this, because the idea is similar for secondary and tertiary, which I'll show you shortly. Now see what is happening here. I'm interested in the maximum value of this 2 phi at which rainbow is forming. Why I want to maximize 2 phi, I wanted to emphasize this in the previous demonstration itself. So let me just once go back to the previous demonstration. Just let me why I want to maximize 2 phi. You see, let me show you in this demonstration what's happening by maximizing this angle of deviation. So let me increase the number of rays once again. I hope it's being captured in the OBS. Yes. Yeah. So let me increase the number of rays, and let me again make the incidence angle. Or otherwise, you see where these rays are getting parallel. See, let me make it horizontal once again. Incidence angle. Let me make it 0 degree. Yeah. So you see the in the end. So this ray incident rays are initially horizontal. Okay. So the place where these rays are parallel, you see the angle of deviation is maximum. For the last rays, if you see, the angle of deviation is maximum. Why? Because until this time the rays are going lower and lower and lower, and then suddenly they start going higher. So that means what? The angle between the incident ray and the emergent ray is maximum for the place where the rainbow is being formed, right? So that's why I need to maximize this whole angle, and this is the angle that I'm calling 2 phi. So let me go back to the previous handouts. I hope you understood why I want to maximize angle 2 phi, because that's the place of reversal, right? Wherever this angle of deviation is becoming maximum, or rather angle between the incident and the exiting light becomes maximum, there that is the location of the rainbow. So let me go back to the my explanation window again. So okay, so back to the explanation window. So I hope you understood why I want to maximize this 2 phi. I mean, maximizing 2 phi means maximizing phi. Okay, so I'm making this in the symmetric configuration. Okay, so now consider this diagram, ray diagram. If this angle is beta, then this angle is also beta. Why? Because this is also radius, this is also radius, so this makes it an isosceles triangle, right? So this is beta, this is beta, and if these two are beta, then this angle automatically becomes 2 beta, and this is the normal, right? This is the normal, and if this angle is 2 beta, then this whole angle also becomes 2 beta. Why? Because you see angles in L shape are equal. So this is L shape, and this whole thing is going in L shape, right? So these two angles are equal, and this angle is 2 beta, so this whole is 2 beta, but this is phi, so this angle is 2 beta minus phi. So here the angle of incidence becomes 2 beta minus phi, right? And angle of refraction becomes beta. So now what I can do, I can just apply the Snell's law. So let me apply Snell's law. Let's see. So what is phi as a function of angle beta? You see, sine of so here there is air, so I can say 1 into sine of 2 beta minus phi, this angle 1 into sine of 2 beta minus phi, that should be equal to refractive index of water is 4 by 3, so 4 by 3 into sine beta, right? And now I want to maximize phi. Why? Because at the maximum value of phi, the rays are somewhere becoming convergent from divergent, or we can say at maximum phi this is parallel. Okay, so if you solve for phi, just you rearrange this equation, so you'll get in sine inverse, this is the angle phi, and then what do you do for maximization? You just differentiate it and put it equal to 0. Okay, by the way, Morin has also shown the plot of phi versus beta. So what's the significance of phi versus beta? So here you see for different values of beta, we are getting the same value of phi. That means so many rays are becoming parallel over here. Phi is not changing. Okay. So phi has got maximum value. If you just differentiate, I will not just claim this. If you just differentiate this equation, so sine inverse this one, if you just differentiate this and solve, so you get derivative phi derivative 0. If you put, then this is what you get. And if you solve this equation, you get uh, beta maximum, and the beta for which phi is maximum happens to be 40.2 degree, and the corresponding value of phi, I am interested in corresponding value of phi, right? So that happens to be 21 degree, okay, approximately 21 degree. And therefore what is the direction in which you will see the rainbow? See, sunlight is coming from here, and this whole angle then becomes 2 phi, which is 42 degrees. So with respect to the line joining the sun to the raindrop, you will see the rainbow at an angle of 42 degree. Why? Because phi maximum comes out to be 21 degrees. So I hope you understood the primary rainbow thing, right? Now I can do the same thing for the secondary rainbow also, similar kind of ray diagram. I'm not spending much time on primary now. So I'll see the secondary rainbow diagram, okay. So in secondary rainbow, again, if the sun is behind, so diagram, so this will be the incident sunlight, and two reflections are going on inside, and it will be going like this. But again, for easy comprehension, I've just rotated this figure a little bit, and uh, here okay, here we'll see what's the angle phi here for what is the maximum angle of 2 phi. Again we'll find out maximum or minimum. Basically we want the extremum for the rays to become parallel, where the concentration of rays is maximum, okay. So once again, if you see here is the incident ray, it gets reflected, and again it gets reflected, and again it here again refracted, and it comes back again at phi angle with the horizontal, okay. Drawing the diagram in the symmetrical location, okay. So now once again, let's say this angle is beta. If this angle is beta, this again is beta, okay. And this is vertical by symmetry, and therefore this angle is 90 degree, and this angle becomes 90 degree minus beta then. So this is beta, and this is 90 minus beta. This one is beta, and this one is beta, so this becomes 180 minus 2 beta. So 90 minus beta plus 180 minus 2 beta, and the sum of these three must be 180 degree, right? Because it becomes a straight line, and therefore you subtract from 180 this angle and this angle, and you get this angle as 3 beta minus 90 degree, right? And again, angles in L shape are equal, so this angle and this angle are equal, and so this is 3 beta minus 90. That means what? This angle is also 3 beta minus 90, okay. So what's the angle of incidence again? So this is 3 beta minus 90, means this angle is also 3 beta minus 90, right? And this is phi, so, and this is the normal, so this whole angle of incidence becomes what? 3 beta minus 90 degree plus phi. So that's what I've written. The sine of, now Snell's law we are applying, okay. So sine of 3 beta minus 90 degree plus phi is equal to 4 by 3 sine beta. See, this angle is again beta with the normal, right? So all this is beta, this is beta, this is beta, all of them are isosceles triangles, right? And angle of incidence is angle of reflection everywhere. So this whole angle becomes then 3 beta minus 90 plus phi, just like this whole angle becomes 3 beta minus 90 plus phi, and that's 4 by 3 sine beta. Once again, what we do, we optimize phi, we make the derivative of phi 0, rearrange this equation and make the derivative of phi equal to 0. And if you do that, what do you get? The value of beta you get is 45.4, but we're interested in corresponding value of phi. So corresponding value of phi happens to be a minimum, and that is 25.4 degree, right? So if this is 25.4 degree, then you need 2 phi. Why? Because now look at the rotated diagram. So this is light coming from sun. So sun is at the horizon, and this is the direction of the final direction in which you are getting the most intense light, right? And this is the double of 25.8 degree, okay. So angle between this line and this line will be double of 25.8 degree. Why? Because this is just 25.8, and that comes 25.4, sorry. So double of that comes out to be 51 degrees. So therefore you should be able to see secondary rainbow at an angle of 51 degree with the horizontal, okay. So let me just show here. So if the observer is somewhere over here, let's say observer is somewhere over here, then this angle will be about 51 degree, okay. Sun is somewhere over here, so from here sunlight is going like this, and here we can see the rainbow, okay. This is 51 degree almost. Okay, so I hope you got how the secondary rainbow is being formed. Most intense light is coming at 51 degree with the horizontal. Okay, now let us extend the same reasoning to the tertiary rainbow as well. Okay, so let's see for the tertiary rainbow. So let me just pan it a little bit. Let me go to the next page. Okay, now for tertiary rainbow, what's the diagram? Once again, I have shown the diagram in both orientation. Here the sun is at the horizon in this diagram on the right side, and on the left side I've shown the same diagram in a symmetric orientation. Okay, so let's try to understand this one. So here this is the incident light, and this undergoes first reflection, then it undergoes second reflection, then it goes third reflection, and then again it gets refracted and symmetrically goes like this. Okay, so this is the diagram in the horizontal symmetry line orientation. Okay, but when the sun is at the horizon, actually this is what's going to happen, right? So now what's happening here, you see, once again, suppose this angle is beta, then this angle is again beta. Okay, and this angle becomes 180 minus 2 beta. So if this is 180 minus 2 beta and this is beta again, this angle is again beta. Why? All of them are isosceles triangles, right? And this is again 180 minus 2 beta. So 180 minus 2 beta, 180 minus 2 beta, and you to get this angle, you subtract the other two, summation of other two angles from 180. So you get this angle as 4 beta minus 180 degree, right? And this angle is 4 beta minus 180 degree means what? If you extend this normal, so then this small angle is also 4 beta minus 180 degree, right? And similarly you can draw over here for incident light, this angle is again 4 beta minus 180 degree. Similar, I mean symmetric diagram you will get here. So what is the angle of incidence now? So if you see, either you take the angle of emergent ray with the normal at the angle of emergence, or you take incident ray angle with the angle of incidence. It's one and the same thing. So for simplicity, from this figure it's easier to see that the angle of emergent ray with the normal, if you see, angle of emergent ray with the normal, this is 4 beta minus 180 and this is 5. So it is 4 beta minus 180 degree plus 5. Okay, now again we apply Snell's law. So sine of 4 beta minus 180 degree plus 5 should be equal to 4 by 3 sine beta. So once again solve for phi and make the derivative 0, so that we know where the rays are parallel. Okay, so if you calculate that, you get phi minimum as 69.2 degree. So 69.2 degree, you take the double of this, and this comes out to be how much? This comes out to be 2 phi comes out to be 138 degree. Now 138 degree, we can try to think of the reasons why it is not visible. The tertiary rainbow is very difficult to observe. So let's see the significance of this 138 degree. So let me again pan things a little bit, go back to the figure. You see, 138 degree is which angle? See, sunlight is coming from here, and then final emergent ray is coming at this angle is 138 degree, right? So that means what? This to see this the light coming from this raindrop, you must be seeing from here, right? You to look at this ray, you should be the observer should be somewhere over here, and here is the sun. So that means what? You are facing the sun. To see the tertiary rainbow, you will be facing towards the sun, right? And that's why this will appear to be dim. So tertiary rainbow becomes very dim. Why? Because all these reflections, they are partial reflections, right? So partially the light is getting transmitted at each of these points, and then rest of it is getting reflected, again partial transmission, then rest of it is getting reflected, again partial transmission. So by the time there are 3 reflections, already lot of light is already lost through refractions at various surfaces, right? And that's why firstly this tertiary rainbow will be very dim because of loss of light. And the second thing is, even if it is there with sufficient light, it will be difficult to see because you will be facing the sun, and because of sunlight it will get washed out. Okay, so that's why we are not able to see the tertiary rainbow. So I hope you understood this one. Then uh, we can also talk about nth order rainbow. I will not get into the maths of it, but you can see some kind of a pattern happening here. So you saw primary, you saw secondary, you saw tertiary, and the main idea is to again and again that we are using is that inside all these are isosceles triangles. So you can talk about the 4th order, 5th order, and nth order. You can find out using a little geometry and maybe kind of mathematical induction, and you can find out how to figure out the angle of nth order rainbow. Okay, so if you want, I'll give you the I'll be posting the link to this paper in the description box, and you can see it from there. It's a very interesting paper explaining rainbow formation very nicely. So I hope you were able to understand how secondary and tertiary rainbows are formed. And now uh, okay, so yeah, so I hope you were able to understand this, and with this I come to the end of this presentation, and I hope you enjoyed this. If you did like the video, please do give it a thumbs up, and please share this video as much as possible with your friends through WhatsApp, Telegram, or Discord, or whatever medium you use for networking with your fellow students for JE or Olympiads. And most importantly, if you have not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to do a new video every day. And thanks a lot for watching this video, and I'll see you in the next one. And as always, God bless you all. Thank you.